Okay, I think I am able to hear everyone. So sorry for the inconvenience. So let's start today class. Let me take the pen. Okay. So let me check it. So good evening everyone. So today let's start the class. Myself Subhankar Mandal from ISC Bangalore. This is the NPTEL online certificate course on analytical chemistry. So the course instructor is Professor Devasis Rai. So almost we are end of the class. Now we are in week 11. So this is the continuation class of electrochemical method part 3. So earlier class we have discussed the introductory part of the electrochemistry and the potentiometric titration, how we can alternatively measure the what is called equivalent point or analytical chemistry point of view without using any colorimetric agent or something. So we can measure the equivalent point by instrumental method or electrochemical method. So now today we more details about the what is called the voltammetric method. So basically what is the voltammetric method basically a set of electroanalytical method where we can measure the current of the analyte by applying the potential at the what is called electrochemical cell. So basically it is developed in early 1920th century, and it is what is called Herovsky first innovated the polarography. From there, it is developed along the voltammetry or voltamogram. So, voltammetry, what is called techniques. So, polarogram basically we have there means they have used the hanging mercury electrode. So, basically, with what is called experiment they the mercury electrode on the in the analyte solution. So and as mercury is toxic and it is not so proper. So for this in modern electrochemistry we have used other electrochemical sets. So basically we have measured the current as a function of voltammetry, what is called potential, applied potential. So and this applied potential you can measure or apply in the system in different form, or you can what is called excite the system in different form, and that is one is variable potential excitation, what is called on the, and this excitation of the potential what where we can apply in the working electrode. So we will discuss more details in the electrochemical cell and what is what is called working electrode, what are the reference electrode. We already discussed about the reference electrodes, but we will discuss more details on the working and counter electrode, what are the function of this in next few slides. So and now we will discuss how or what type of excitation of voltammetry we can use. So this is basically first one is the linear scan. Basically this type of excitation you usually use in polarography. So basically there we are what is called applying the potential as a function of time, and potential we are linearly or as a constant rate we are applying in the system. So and this is basically for this with time whatever potential, suppose in the initial state you have the potential of the system is E1, and after 1 second you have applied another E1. So basically you are applying a constant potential with second or with time. So and after that whatever potential is here, this point, that is E1 plus E2. So that way you are linearly applying the potential in your system. So this linear scan call, and this method of voltammetry is the polarography or hydrodynamic voltammetry. So next one is the pulse method. Basically this is the differential pulse voltammetry. So we already learned that what is called linear pulse voltammetry. For the, basically suppose we have a system as a particular energy or particular potential, and you are applying some pulse of potential for a few time, and after that when you will give the relaxation, it will come in the initial state. Again you are applying the potential and it is increasing like this, and after that when you are giving the relaxation time, it is coming on the initial or baseline. So and this one is the del E, whatever you are increasing the potential of your system. So this is what is called the normal pulse voltammetry. So but in the differential pulse voltammetry, what you are doing, you are staircase, you are applying the potential and it is going, and at a particular time you are applying the potential, suppose this is tau, and then after that you are giving the relaxation for the few minutes. Again you are applying the same amount of what is called potential, and you are not allowing the system to go to the baseline whatever you have given or you have observed in the normal pulse voltammetry. So this differential pulse voltammetry, basically you are differentiating the current, and you can get some two experiment or two reaction, electron transfer reaction, which is much more closer to each other. So that case you use the differential pulse voltammetry so that you can differentiate two redox process separately or prominently in voltammogram. So next key excitation method is the square wave pulse voltammetry. So here we are basically applying the potential and as a square form. So basically here whatever potential you are applying in every state of experiment, you are or pulse, you are giving same amount of potential to each step. So this is the square wave voltammetry. So we will discuss more details about square wave and DPB in later class, or maybe next class. So today we will discuss more about the cyclic voltammetry, which is a trigonal excitement of the potential. So basically you are sweeping the potential from some initial state A to, and it is going to B. Again you are going to the initial state of the your system or whatever state you are started, in that potential you are coming. So if you what is called measure the potential as a function of time, then you will get a triangular type of thing. So this is called the cyclic voltammogram. So basically your voltammogram is completing the cycle of one linear scan. So this is the thing. So what is the key thing? So before we will discuss more details today on the cyclic voltammogram. So basically cyclic voltammogram, before going to the more details about the cyclic voltammogram, we will discuss about the electron transfer. So there is two type of electron transfer reaction. One is homogeneous electron transfer, other one is heterogeneous electron transfer. So homogeneous electron transfer, basically suppose you have two component, one is ferrocene suppose and or other one is cobaltocene. So and both these component are in the solution. So these two are in the same phase. So as it is in same phase, for this it is called homogeneous. So in same phase, and if you mix these two, then you will see that cobalt is what is called transferring the electron to the ferrocene, and it can reduce the ferrocene, and it cobalt itself, cobaltocene can itself oxidize. So now question, why this is happening? Why cobaltocene can reduce ferrocene when it is there, both of these chemicals are in the same solution? So the answer is because if you see the HOMO and LUMO, so the HOMO of the cobaltocene energy is higher compared to the LUMO what is the lower unoccupied molecular orbital of the ferrocene is lower energy. So as you know that higher energy, from higher energy to lower energy electron can transfer so that it can stabilize. So cobaltocene can transfer the electron to the ferrocene. For this it can reduce the ferrocene. So now question, what is the heterogeneous electron transfer? So heterogeneous electron transfer basically it is one key, it is not in the same page. So basically in heterogeneous electron transfer what is there, that you have electrode which is a solid and your analyte whatever is there it is in the solution state, and you dipping your what is called working electrode or your counter electrode and or your reference electrode which are in the solution. So these all are the solid state and this is in the solutions too. So for this it is the heterogeneous state or two different phase. So for this it is called the heterogeneous electron transfer because the electron transfer is occurring on the electrode surface which is a solid and your analyte which is in the liquid state. So for this we call the heterogeneous electron transfer reaction. Whatever we are discuss in chemical cell, where we are dipping the electrode or if you want to what is called talking about the electron transfer rate constant, that is called heterogeneous electron transfer rate constant. So if you dipping your what is called electrode in ferrocene solution, and then if you see suppose the electrode energy or is higher than the LUMO energy of the ferrocene, then from electrode uh, one electron can transfer to the ferrocene and it can reduce to KFC. So ferrocenium can reduce to ferrocene. So as a result what is called the this process is called reduction process. So whatever it is there in the electrochemical process, that is all are heterogeneous electron transfer process. So now this is the particular convention of cyclic voltammogram. So where you can see you can start from here and it is increasing the current, and after that it is reach some potential, and after that it is again in the reverse process it is increasing the current and it is coming to the initial state. So in this cyclic voltammogram there is two convention to present your data. That is, one is US convention, another one is IUPAC convention. So in US convention basically your potential axis whatever it is there it is in the x axis. So a higher potential value on the left side and the lower potential value on the on the right side. As a result whatever process is there in the upper process, this current value whatever upper process, that is the what is called reduction process, and in the lower redox peak, that is for due to the oxidation process. And in the IUPAC convention is the reverse of the US convention. So basically here the higher potential is the right side and the lower potential in the left side, and the upper redox peak is due to the oxidation of your analyte, and the lower part is the reduction of the analyte. So now most of the people are obey or use this IUPAC convention because we are more familiar about the right hand side is the positive axis and the lower side or in the left hand side axis is the negative potential. So these two conventions, so in what is called, if you see any literature that one process they are talking that upper redox peak due to the oxidation or reduction, then you have to check that is IUPAC convention or US convention. So basically you have to check the potential axis which order it is there. So this is there. So as we are discussing about the cyclic voltammogram, before this class we also discuss about the Nernst equation, basically how what is the potential or of any redox peak or that things we have discussed. So basically what we have discussed, that E is equal to E naught plus RT ANF ln activity of the activity of the redox. So these things were there. So at that time we did not discuss about the what is the formal potential or what is the half value or half redox potential. So that is we can discuss there. So as this E naught plus RT by NF. So activity we can activity we can write that activity coefficient, suppose E dash by activity coefficient of the redox plus RT by NF ln concentration of the oxidation process and concentration of the redox component. Okay, so this part, so this potential which is called, this is called the formal potential E naught plus RT by NF ln ox by rate. So this is the thing. So Nernst equation basically we call the standard potential. What is the standard potential? When you are measuring any system or of your analyte in the standard condition. Basically, suppose you are measuring, it is in what is called 1 atmosphere pressure or standard 1 atmosphere pressure and temperature. So in that case it is called the standard potential. When we are measuring in our laboratory or something, that time we are not it is not in the standard condition. So we usually people usually prefer this formal potential. So this formal potential basically whatever temperature component also there. So it is more called practical. So this formal potential basically you can measure. Suppose you have what is called some what is called redox couple. So therefore, suppose this is the EP. I will always use the IUPAC convention. So this is the EPC, that means cathodic redox peak, and this is the anodic redox peak. So E half basically formal potential basically EPC plus EPA divided by 2. So this is the what is called Nernst equation, and from here we can get to know what is the formal potential and what is the applied potential. So these things is there, and we also discuss about the current value when we will discuss the potentiometric titration. So basically there is three different type of current value usually we have discussed. One is, where is my cursor? So basically there is three type of current we have discussed. One is diffusion current, one is migration current, one is convection current. So so now diffusion current, here I want to mention one thing is that diffusion current, whatever in cyclic voltammogram, whatever current you are seeing or we are measuring, that is the diffusion current. So basically as we are measuring diffusion current, then how we are what is called compensating or minimizing these other two current. Okay, so this convection current basically what we have know that due to the steering or physical violence whatever disturbance is there, due to that this convection current is to come. So if your system or whatever experiment you are doing that is in the static condition, then you can minimize the convection current. Okay, and now migration current, how you can measure minimize that, you can use supporting electrolyte, so that so that you can minimize the migration of your analyte. So this supporting electrolyte, what is the function of supporting electrolyte, and which type of element you can use this supporting as a supporting electrolyte, that things we will discuss in the next slide. So basically whatever I want to mention here, that whatever cyclic voltammogram we are measuring, that is what is called a diffusion control current you are measuring. So basically this is the standard kind of electrochemical cell where you can see a glass container is there. So this is the glass container is there where you can dip three electrode. One is what is called working electrode, one is working electrode, and one is counter electrode, one is reference electrode. So basically we have already discussed that what is called we have cathode and anode. So basically you have two electrode system. Suppose you have two electrode system, one is cathode and one is anode. So basically when we are measuring the potential of these two, then you can get the redox peak also. But why this third electrode is required? One is that is auxiliary electrode or counter electrode. Basically also we discussed that when you are measuring the potential or some reaction is happening on the cathode side, suppose some oxidation is happening, that means in your system somewhere it should be reduction is happening. So as you are transferring the electron through the reference electrode, that means you are transferring the current through the reference electrode. As a result, on that reference electrode surface some reaction is happening, that is the reduction. What is the this is the opposite reaction of the oxidation. So as the reaction is happening on the electrode surface, that means its potential is not constant. So whatever potential you are measuring with respect to the reference electrode or cathode or anode or two electrode system, that potential is not fixed. So for this whatever potential you are getting, that is not a actual potential. For this we need three electrode system. So three electrode system, basically what is there, you have some auxiliary or counter electrode, and you are measuring the potential along these two, reference electrode and working electrode, and you are measuring the current through working electrode and counter electrode. So the whatever electron process is happening through the counter electrode and working electrode, so what the potential of the reference electrode is remain constant. So whatever potential you are measuring on the working electrode, that is remain constant. So for this three electrode system is required to study some kinetic study or some fundamental study. Usually you prefer the three electrode system. So now question, what kind of solvent you can use for your experiment. So a good solvent for characteristic in electrochemical cell or electrochemical analysis, that is the experiment, this liquid should be stable in the experimental temperature. Other thing is whatever analyte you want to measure, that one you have to it has to dissolve in the analyte in the solvent. So that means suppose you want to measure, you have synthesized some new compound and you want to what is called do some cyclic voltammogram, then you have to check first it is soluble in that solvent or not. Then other thing is the stable towards the oxidation or reduction potential of that analyte. That means you have to check first that your solvent is stable in that potential window or not. So for this you have to first check that stability window of your solvent. Other thing is it does not lead to deleterious reaction with the analyte or supporting analyte. So whatever we have discussed, that to minimize the migration current we have to we use supporting electrolyte. So your solvent should not react with the supporting electrolyte as well as in your with your analyte also. So and it should be purified. So now we have discussing of the supporting electrolyte. So what is the criteria of supporting electrolyte? So supporting electrolyte should be highly soluble in the solvent, and it should be chemically and electrochemically inert condition in the experimental condition, and it should be purified. So now what type of working electron we can use? So working electrode basically usually use working electrode basically glassy carbon you can use, glassy carbon or platinum working electrode we can use. And what kind of reference electrode we have used? Different type of reference electrode we have discussed, that saturated caramel electrode or AgAgCl electrode, or standard hydrogen electrode you can use. But in this case standard hydrogen electrode usually people cannot not use in the what is called experimental laboratory. So basically saturated caramel electrode or AgAgCl or non-aqueous AgAg plus electrode also people use for their experiment. So and the counter electrode basically carbon electrode or platinum wire people use in their experiments. So this is the experimental setup of your what is called experiment. And now question, suppose you are using working electrode in your system and next person want to use that same electrode. That means there may be some possibility of impurity on the electrode surface. Then how we can clean that thing? So this is basically that case. Basic carbon electrode or glassy carbon whatever is there, that is what is called highly any organic component can absorb on the electrode surface. So basically some polishing pad is there, and on that aluminum water slurry people use, and on that people make what is called English 8 draw 8 for few times, so that all every what is called direction it can be polished effectively. So people usually make circle on this, so that is not the right way to cleaning the electrode, working electrode. So you have to make, or you can draw the working electrode English 8, so that all the direction your working electrode can be clean. So now question is what are the step we can follow to acquire the data when you are doing some experiment in your laboratory. Okay, so the first thing is the recording background scan. Basically what we have already discussed, that suppose you are using some solvent, so and your redox peak you want to see some analyte, and you have to first check in that potential window your what is called solvent or your supporting electrolyte is stable or not. So that is the background scan. So you have to first check in that potential your solvent is stable or not. Now second one is the importance of the inert atmosphere. Basically if your analyte is some oxygen gas or some other CO2 or CO carbon monoxide gas is there, then it can affect you in your what is called in your experiment. So for this to remove other gas, you can purge your system with what is called nitrogen gas or some inert gas, argon gas you can purge, so that other gas can remove from your system, and you can keep you can do the experiment in the inert condition. So in this system these two gas what is called hole is there, so from there you can purge your system with some inert gas. Another things is the measure the open circuit potential. So basically I'll discuss these things in next slide also. So basically we are starting what is called some scan on the one point, and then you are going some potential, or here what is called here you can see that in their arrow chino arrow mark is showing. So these things it is starting from here and it is going to the this point, and it is again coming to this point. So how we can get to know that suppose you are doing some unknown system and you are doing something some cyclic voltammogram, then how we can get to know that from which potential we should start. So for this, before starting your experiment, we have to measure the open circuit potential or OCB value. From there we have to start the experiment. So basically OCB value, basically when you are not applying any potential, whatever at the equilibrium state before starting the experiment, whatever potential is there or whatever potential difference between the reference electrode and working electrode, that is called the OCB or open circuit potential. Another one is the minimizing the ohmic drop. So basically when you are measuring the potential in the reference electrode and working electrode, there is some solution resistance is there between the working electrode and what is called counter electrode. So in this solution resistance there is two parts there. One is uncompensated resistance, other one is the compensated resistance. So this compensated resistance, whatever instrument you are using nowadays, that is potentiostat. So this potentiostat can minimize this compensated resistance, but this uncompensated resistance, which is between the working electrode and reference electrode, that cannot be compensated. So for this, people whatever usually do, they can measure the resistance between the what is called working electrode and reference electrode, and they can manually subtract from the whatever potential we are getting that thing. So that is the compensated resistance. So people usually do some impedance spectroscopy between in the three electrode system, so they can get this type of system. So and from there they can minimize or compensate manually this whatever resistance is there. So from there they can compensate the potential. So this potential, uncompensated potential, whatever is there, due to that whatever potential you are observing, suppose you are doing some redox process, some Fe2 plus to Fe3 plus, and whatever potential, suppose it is coming 0.77 volt or something, whatever potential, it may not come at that potential, it may be 0. What is called 79 or some volt is coming. So this difference whatever is there due to the this uncompensated resistance, due to that your potential difference is coming. So these things you can what is called minimize by manually to measuring the what is called before doing the experiment. You can measure the some impedance spectra and you can measure the uncompensated resistance. Okay, so these things is there. Now we already discussed that typical cyclic voltammogram or trigonal voltage excitation we are using. So and these things we are starting, suppose A whatever it is there, and you are scanning the potential with time, and your potential is coming and your cyclic voltammogram or current response is coming like this, and after sometimes it is suddenly increase at a particular maximum point C, then again it is coming down and it is reaching D when you are reach here. Again when you are doing the reverse process, it is coming and again it is giving the maximum current E, and again it is coming to the G point. Okay, so this is from here some question you can it can arise that whatever some redox process is going on, so what is the driving force of this reaction? So first question is this, the what is the driving force of this reaction. Second question is why this cyclic voltammogram is shape like dark shape like structure, why not different kind of structure, why not this trigonal kind of structure is not showing. So why it is with potential the current response is dark shape. Okay, so next question is why this peak is coming at a particular potential, and the fourth question is after maximum, that is C point, why it is depletion is going on. So it can be like this, then it can go like this or like this, why this depletion is going on. So and another question is the reverse process. So suppose this is the redox process of something, and this is the reduction, and this is the oxidation. So why it is there some depletion or some shift is there, means whatever redox peak is coming, that reverse process, why the reverse process the peak position is not coming in the same k potential whatever it is coming the C. That means the E, C and A position is not same k potential position. So the question is why it is not in the same position. So the next question is the where we can start this A point, where we can start the experiment. So basically this question answer we already discussed, that we should start from the OCB value, because whatever your system is, it is in the ground state. So you should start from the ground state. Otherwise, suppose you don't know what is there in your analyte. So suppose you have some new compound, and you are starting some random potential, and in that potential your component some intermediate state or some excited state it can reach. So whatever initial state or ground state it is there, that you cannot find or you cannot determine from the cyclic voltammogram. Okay, so for this you should start from the what is called from OCB value. So another question is B and C E potential, which is known as the E half potential. So what is happening here? So E and B, this potential, what is happening? So and what is the importance of scan rate? Basically we are scanning here the potential as a function of time. So what is the importance of this scan rate? So all this question, if you see this voltammogram, so all this question can come in your mind. So we will discuss one by one by time. So basically first question is what is the driving force of the reaction. So basically as I have discussed that in the first one, so basically you have the electrode and you dipping in your electrolyte solution. So basically can it is connected with the potentiostat. So basically the function of potentiostat is it can modulate your potential or energy of your electrode electrode working electrode. So if you want to do the reduction of your analyte, or you want to reduce your analyte, then you can increase the energy of your electrode, so that it can donate the electron from the donate the electron from the electrode to the analyte. So the driving force of the reaction is the potential, applied potential from the what is called potentiostat. Okay, now question is why are there is peak. So this peak due to the what is called electron transfer process. So basically you have some analyte, suppose Fe2 plus is there, Fe3 plus is there, and you are reducing, so this is Fe2 plus is going. So due to the electron transfer, the redox peak is coming. So for this there is increase in the current value. So basically you have the electrode surface, and you have some energy, and on the bulk solution you have the analyte. So there is the Gaussian probability function is there. Basically it is like this. So initially what is there, that when your potential energy is here, electrode energy, suppose this is the E1 and this is E2 and this is E3 and this is E4. Okay, so when you are in the E1 state, that is basically in this region, so there is basically no analyte energy is matching. So as a result there is no current value is there. When it is coming to the E2 state, there is some probability is there where the analyte is coming on the electrode surface and it is reducing to Fe2 plus. So as a result your what is called energy current value is some more here, so this is increasing. And after that, at the E3, where the maximum probability of matching the energy of the electrode and of your analyte, so the electron can transfer easily from the electrode to your analyte. As a result, it is showing the maximum current. Okay, after that it is decreasing due to the diffusion process. So why this is depletion is there, which we have asked in the question number what is called 4, that why after maximum depletion is there. So as we have discussed earlier also, that this is the diffusion process. So basically diffusion due to the concentration variant, concentration what is called variation. So basically whatever is there, so if you see, this is your electrode surface and this is your bulk concentration. So basically when it is the initial state, your what is called Fe3 plus is there, all the solution Fe3 plus is there. Okay, so then when you are applying the potential, Fe3 plus is coming to your electrode surface. So as a result, some on your electrode surface, Fe3 plus concentration is, Fe2 plus concentration is increasing. So that means in this region on the electrode surface, on the bulk solution, there is some concentration variation is there. So due to this, the Fe3 plus can diffuse from the bulk solution to the electrode surface. Now at a particular time, after maximum capability, there is what is called the probability of coming Fe3 plus to Fe2 plus, Fe3 plus, the probability of coming Fe3 plus to the electrode surface is decreasing. As a result, the ability of the Fe3 plus on the electrode surface also decreasing. For this, it is current value is what is called decreasing. So and other thing is this, as we know that this current value is correspond to the concentration of the analyte. So if the analyte concentration is increasing, then your current value also will increase. Okay, so that things we'll discuss from the we can get the from the Randless equation, which we'll discuss in the next slide maybe. So this thing is there. Now questions, this area of this cyclovoltammogram. So from here, what kind of information we can get? So basically, if you see that if you measure this one as a function of time, so basically you are getting like this. So whatever time region is there, so basically whatever time region is there, if you I versus t, so we know that q is equal to it. So for this, in this area, you can get that how much charge is required to reduce your your what is called Fe3 plus to Fe2 plus. How much amount of Fe3 plus can what is called converted to Fe3 plus, Fe2 plus. So that information you can get from this area. So basically charge and if you get to know the charge, then you can what is called from the Faraday rods, you can get to know that how much or how many molars of Fe3 plus can reduced in this one cycle of your cyclic voltammogram. So these things is there. Now we already we get to know that this depletion due to the diffusion, and duct shape also due to the diffusion, and maximum probability of the what is called Gaussian probability reduction of the Fe2 plus. And then in the now question is, why in the reverse process the peak is shifted. That means I am asking the question that why this peak is not coming on in this position, it is little bit shifted. So the answer is that when your when you are reaching in the in the what is called D point, that means on the electrode surface all the Fe2 plus is there, and as it is diffusion process, that means after some times when you are scanning in this region, that means Fe2 plus is going to the bulk solution. So as it is diffusion process, that means your concentration of the Fe2 plus on the bulk solution is less, so that Fe3 plus is going to Fe2 plus, again this Fe2 plus is going to the bulk solution. When you are doing reverse process, that means similar process is coming, so Fe2 plus is there in the bulk solution. When you are doing reverse process, that means it is diffused to the electrode surface. So when it is diffusing, it will take time to reach the electrode surface. For this, it is what is called not coming in the this position of potential, it is shifted to key E point. So for this, it is key what is called not coming, as it is reverse process. Okay, although it is reverse process, but it is not coming in the same position, it is a little bit shifted towards the okay, high potential during the oxidation. So due to the diffusion okay, or okay, unavailability of the Fe2 plus on the electrode surface, it is shifted. So this is there. Now what is happening in the B and E? So basically in this B and E, so what is happening, that is basically E half. So as you know that from the what is called Nernst equation, E is equal to E naught plus what is called RT by NF ln ox by redox process. So basically E half, when it will be the reverse process, as it is reversible process, that means whatever forward reaction is there and the backward reaction, the concentration of the for oxidate and reduce process is same. It is a reduction product is same, that means reactant and product concentration is same. So this process what is called, it is in the equilibrium, and at that process, at that condition, E is equal to E half. So that means in this potential what is called B and E point, your what is called reactant and product concentration is the same. Now what is the importance of the scan rate? So basically if you scan your system, or you can part of your system at different potential rate. Suppose one state you are what is called perturbing at 5 millivolt per second. Other one you are what is called scanning 10 millivolt per second, and another one 30 millivolt per second. So basically in different scan rate you are what is called applying the potential in your system. So basically in that case, what is the importance of this scanning rate? So basically in that case, if you do different scan rate, then you get different potential graph like this. If it is what is called reversible process, then with potential the current value will increase. So basically it will increase, and suppose, so suppose this is 5 millivolt, this is 10, and this is 30. So basically with scan rate, your what is called potential will current value will increase, which we can get the information from the Rayleigh equation. So basically Rayleigh equation, peak current as a function of peak current as a function of scan rate. So this is the Rayleigh equation, where n is the number of electron of the redox process, and A is the Faraday constant, A is the area of the working electrode, and C is the concentration, bulk concentration of your analyte. Okay, and nu is the what is called nu is the scan rate, and d is the diffusion coefficient. So with scan rate, if you measure, that is ip, as a if you plot ip versus nu of the scan rate, then you will get, if it is a reversible process, then you will get a straight line. Suppose this kind of thing, this is ip peak current versus mu to the 2, and from the slope you can get what information, the diffusion coefficient of your analyte. So we basically also you can get suppose the number of electron of your redox process. So basically, if you can know that other parameter, if Faraday constant and area of your electrode, and bulk concentration of your analyte, then and if you know the diffusion coefficient of your analyte, or you know the n, then you can get to know other key parameter. Means if you know the diffusion coefficient, you don't know the number of electron, then you can calculate number of electron, or if you know the number of electron, then you can calculate the diffusion coefficient. So I have one video on this, means the practical video to calculate the diffusion coefficient. So I will upload that video on the Google Drive, so you people can access that video and you can go watch that video. So and this is the thing. Now the other question is the reversibility. So on process, whatever redox peak we have observed, that is what is called reversible process or irreversible process or quasi-reversible process. So how we can decide that one process is reversible or irreversible or quasi-reversible? So the condition of the reversible or irreversible process is the peak potential separation. So if the peak separation of the cathodic, anodic and cathodic is 0.0592 by n volt, then or less than of this, then it is a reversible process. Other condition is the if the peak current of the anodic and is equal to peak current of the cathodic. If peak current is the cathodic is same, then that is also reversible process. And what is the irreversible process? In irreversible process, IPA not equal to IPC. That means the current value of the cathodic process is not equal to the current value of the anodic process. And other thing is you cannot and the in cyclic voltammogram you can see on redox peak, and other case you did not observe any redox peak for the reverse process. So this is also the signature of the what is called irreversible process. That means whatever time scale you are measuring the cyclic voltammogram, in that time scale your product is not stable, so it converting some other product, or it can convert to the initial product chemically. So as a result, we are not observing any redox peak due to the reverse process, means due to the reverse process. So that is the irreversible process, and in this case the EP peak potential separation is will be quite high. So and other one is the quasi-reversible. Quasi-reversible is the process is basically your redox process is there, but this redox peak separation is higher compared to whatever reversible process condition. So basically this del EP is greater than 0.0592 by 2. And other thing is this peak potential for the cathodic and anodic process is not same. Okay, so the redox peak is there, but the cathodic and anodic peak position is means current value is not same. So what is called this condition, actually this condition for the quasi-reversible process. So irreversible process, there is no reverse redox peak is there, so basically only one redox peak is there. So this is the condition for and from cyclic voltammogram you can get to know that if any process, that is reversible process or irreversible process or quasi reversible process, so that information you can get. Now square wave voltammetry, what we have discussed some introduction part I just introduced. So basically in the square wave you are applying voltage pass for quite sometime, then sometime, and then you are giving the relaxation and it is coming some potential. So basically in square format you can see in the square format you are applying the potential and relaxation time. So and this potential is the tau, and whatever increase the potential, that is del E, and if you measure the current del I as a function of potential, then you will get the redox peak of the of your analyte. So basically in this case, suppose whatever I have discussed in the for the previous slide, that if your system is quasi reversible or what is called irreversible process, and you are not able to see any redox peak due to during the reverse process, then you can do square wave voltammogram, which is some 5 to 50 what is called millisecond time scale, where the cyclic voltammogram 5 what is called 0.5 to 5 second scale. So that means this time scale is quite small. So at in this case it will help to what is called monitor some redox process, which is quite time scale of the transformation or reaction is quite low. And other thing is, if your analyte concentration is quite low, then in that case also you can use this what is called square wave voltammetry or differential pulse voltammetry. So that case you will observe the what is called redox peak of the reverse process for quasi reversible or irreversible process. So for these people can now use the square wave voltammetry or differential pulse voltammetry to know more details or more accurate information for the redox process. Okay, so now we can discuss some question that on the previous year, what is called assignment questions. So I can wait for 30 seconds, and these all are very easy questions, so we can discuss all these questions. Okay, so first question is, the what type of process is used for determination of the chloride in blood serum or plasma? So if people can write in the chat box so that I can see, and I can discuss also. So there is four options: voltammetric, conductometric, potentiometric, and coulometric. So what type of process is used to determination of the chloride? So as chloride means halide is there, so that means you have to think we already know something about the silver plus ion. So silver plus ion can react with chlorine or bromine and it can precipitate. So AgCl is it can precipitate. So and that means we have to choose some method which can produce or generate Ag plus. Suppose you dipping some what is called silverware and you applying some current, that is coulometric current means coulometry you are applying, and in that case some silver Ag plus ion is producing, so it can react with the what is called halide ion or chloride or bromide, so and it can precipitate. Due to that you can measure the chloride ion in our blood. blood. So the answer is D, coulometric. Okay. So next question is, what is measured in amperometry or amperometry or amperometric titration? The change in current, the change in potential, the change in concentration, change in capacitance. Okay. Sunil has written change in current. So, yeah, so that is the correct answer. So amperometry means you are measuring what is called current as a function of time, or function of titration means function of some analyte you are using in the solution, adding some titrant in your solution. So with that, how the current value is changing, that you are measuring. So that means the answer is the change in current. Okay. So next question is, fill in the blank with suitable option given below. So in the given cyclic voltammogram, the nature of the redox process is, the process is irreversible, the process is reversible, analyte is adsorbed onto the electrosurface, are instrumental for. So what is the answer? So it is, Sunil has written, it is a reversible process. Yeah, it is a, although it is reversible process you can say, but it is not what is called, I can say, as it is not mentioned that what is the separation of the peak potential separation. So basically this potential should be 0.0592 by n. So if it is a one electron process, and they did not mention the potential separation, but if it is in between 0.0592 by n, then it is a reversible process, and this peak current during the oxidation and during the reduction is same, then it is same what is called, it is a reversible process. So uh, it is you can say this is a reversible process, but if you think actually, as they have not mentioned anything about the potential value, so it's difficult to say, because from the graph you cannot say that this is a reversible process. So it is reversible, you can answer this thing as a reversible, but if they can mention this potential value, then it's better and you can accurately answer. So what is the use of cyclic voltammetry? Investigate the reduction and oxidation process, measure the pH, initiated the redox reaction, measure the potential. So for question, what is the cyclic voltammeter? Basically, in cyclic voltammeter, whatever you are measuring the reduction and oxidation process, because we are getting the what is called measuring I as a function of E, and we are getting the this kind of graph. That means this is for the, suppose this is what is called positive and this is negative, sorry. So that means this is the oxidation process and this is reduction process. So we are investigating the reduction and oxidation process. We are not measuring here any pH, and also we are, if your system is not any means your system does not contain any redox center, then we will not able to initiate the redox reaction in cyclic voltammeter. Okay. So and the potential, we are applying the potential, we are not measuring the potential, we are applying the potential, and we are measuring the current, what is called responding current by the system. So the answer is A. I think Sunil also written A. Thank you, Sunil. So the fifth question is parathion act as a non-toxic agent, coloring agent, insecticide, and supporting electrolyte in CV. So the answer is C, insecticide, because it can what is called this is the enzyme acetocholine synthase indirectly. So basically, what I can say here that the phosphate ester is more reactive in enzymatic that phospho orthothioate ester it can form, and the phosphorus atom become much more electropositive, so that it can easily react parathion. So this is the answer. And why do we use potential state? So it control the current at working electrode, or it control the voltage difference between a working and reference electrode, or it measures voltage, or all of these. I think I already discussed this one, so in you can answer easily. So yeah, the answer is B, because we already discussed that potential state usually used to modulate the potential of the working electrode, as we are measuring the what is called potential, that potential with respect to the reference electrode. So basically we are controlling the voltage between the what is called between working electrode and reference electrode. So this is the answer. So what is the role of reference electrode in the electrode process? Allow the measurement of the potential at working electrode without passing current through it. Measure the current. Allow to measure both current and potential. Allow to pass current with respect to reference electrode. So the answer is A. So allow the measurement of the potential at a working electrode without passing the current. So we already discussed. Suppose you have this electrode setup, and you have three electrode cell. One is working electrode, one is counter electrode, one is reference electrode. So basically you are measuring the potential between reference electrode and counter electrode, and you are measuring current between the working electrode and counter electrode. So that means the function of a reference electrode is to measure the potential of the working electrode, and the current is passing through the counter electrode. So it is not passing any current through the reference electrode. As a result, its potential remain constant. Okay, so that means the answer is the A. So what are the example of biological sensor? Enzymes, antibody, nucleic acid, all of above. So biological sensor. So biological sensor, what we know is that biological sensor are the device that made up of a transducer and a biological key element. That is, it may be an enzyme, or it may an antibody or nucleic acid. So the biological element interaction with the analyte being what is called tested, and biological response is covered into a electrical signal by the transducer. So basically the answer is the all the above. So in biological sensor, we can use what is called all of above. Enzyme also you can use antibody or nucleic acid also. So these things, I think, when COVID-19 or SARS-CoV came, so people also use spike protein as a what is called spike protein as a what is called transducer and key sensor, biological sensor for, and they have measure cyclic voltammogram, as well as they have measure impedance spectroscopy, that particularly when the coronavirus interacting with the spike protein, there is some response, or decreasing the current value. So from there they particularly what is called use this spike protein as a biological what is called sensor. So spike protein, that means protein is the combination of nucleic acid, so nucleic acid also you can use. So the answer is all the above. Okay. So what are the correct statements for electrochromic device? It control optical properties, used in display or smart window. It generates reversible color change responding to electricity. So the answer A and B, and option B is B and C. Option C is A and C, and D is A, B, C, all the above. So basically electrochromic device, I think I can discuss. The electrochromic device generates a reversible color change responding to the electricity, which are promising candidate in the application of displays, smart windows, and military what is called camouflage, and it controls the optical properties such as optical transmission, absorption, and reflectance or emittance in the continual but reversible manner on application of the voltage. So basically it can use as a optical properties also, and smart window display also. So the answer is D. So all the above statement, whatever it is there, it all are the what is called correct, because it is electrochromic. So basically electron transfer, due to the electron transfer, whatever color change is observed, so that is the thing. So answer is D. Okay. So the next question is, which method is applied to investigate the water quality of COX? So anodic stripping voltammetry, cathodic stripping voltammetry, cyclic voltammetry, all of these. I think last question, Kesunil also mentioned that all of above. So yeah, that is the correct answer. So this what is called sea water, whatever say, so water quality basically in water quality, whatever is there, we usually measure the what is called some cation. So basically chelate 2 plus or calcium 2 plus or thallium 1 plus, this cation usually we measure. So as it is cation, so anodic stripping voltammetry people use. So this anodic stripping voltammetry, basically it can measure nanomolar detection limit. So very low concentration of analyte also you can measure from the anodic stripping voltammetry. So the answer is what is called A is the answer. So I think yeah, and this one is the answer. I think all these three, all the question is there. We already discussed all this thing. I think that's all. We'll discuss next class on the application part and more about this pulse voltammetry. So up to this, I think we can call up the meeting. Thank you all for the joining. I think if anyone has any question, then unmute the mic and you can ask the question. Okay, if anyone has no question, then you can call up the meeting. Thank you everyone for joining the class. So thank you.